Welcome to the lecture on the Cosmoglobe sky model. The Cosmoglobe sky model represents our best estimate of what the sky looks like given the data integrated in the Cosmoglobe framework. In this lecture, I will demonstrate how to download and use the various functionalities included in the Python Cosmoglobe sky model package. My name is Metin San, and I'm a PhD candidate at the University of Oslo, where I'm working on Cosmoglobe. The documentation for Cosmoglobe can be found on cosmoglobe.readthedocs.io, and here you can also find a tutorial on the sky model. We will start by downloading the Cosmoglobe package, which can be downloaded with pip for Python versions greater than or equal to 3.8. Before I start, I want to mention that if you experience any problems with dependencies during the installation, it is likely due to known dependency conflicts between Numba and NumPy. If this is the case for you, then I would suggest creating a fresh new virtual environment and downloading it there. In the following, I will do just that. So let's get started by creating a new Conda environment. So this may take some time. Okay, once the download is complete, let's activate the environment, and then we can do pip install Cosmoglobe. For the sake of this tutorial, I will download IPython when the Cosmoglobe download is complete. Okay, that seems like it worked. Okay, so it looks like everything worked. So let's head into IPython. I'm using this PyLab flag to get some auto-imported stuff and plotting functionality. Okay, so let's start by straight up just importing Cosmoglobe. Since this is the first time we do that, it might take a few seconds. Okay, so now that we have imported Cosmoglobe, I should mention that you essentially need chain file to work with. This will likely change once the Beyond Planck collaboration has released their data. Then we'll make Cosmoglobe's sort of default to that dataset. But for now, you need a custom chain file to work with. But luckily, Cosmoglobe provides a test chain case for this scenario. So we can get that by simply doing this, get test chain, and this will then download and cache a chain for you. So I've done this before on my computer, so it remembers that, but the size of this file is around 1.6 gigabytes. So now that we have our chain, let's print that. So the contents of this chain, it only has 2 samples with 6 components. We can also check the samples like this and the components like this. And in addition to the sample data, there's also a parameters group that contains a lot of information that we need to initialize the sky model, but that isn't necessarily being sampled in Commander. Okay, so the first use case of this chain file is just to inspect what's in it, and we can do that with dictionary syntax as such. So let's head into one of the samples that we saw were present. So if you just type the sample, it will show you what's available in the next path, so you can kind of traverse the chain like this. So let's go into dust. Yeah, and once you hit a data set, it will print the data out for you. Yeah. Let's check another one. AMP LMAX. If you try to inspect some ALMs, that usually takes a second longer because there's some unpacking that needs to be done to the correct heelpix format so that you can directly use this with heelpix. Okay, so in addition to this dictionary lookup, there's a few files that I would like to mention. There's the get function, which essentially does the same thing for all samples. So if we do amp lmax, and we have 2 samples, so this should this should give us 2 of 3000, yeah. You can also specify the samples using either an integer, a list of samples, or the built-in range function. Okay, and next up there's the mean function, and what this does is it averages all of the samples for that value. So similarly for ALMs. And the final function is the load function. So this generates, or this returns a generator. So if you have a large chain and you want to work with the data in it, but you don't want to store it, the intermediate results, you can do a for loop with this function. So for instance, for ALM in print ALM, so this will loop over the values without storing them intermediately. Okay, so that's all I want to cover on the chain object. Now it's time for the sky model. So this chain file, we can feed it into the cosmoglobe.model from chain function. So let's store this in a model, and let's say chain, this is the chain file, and then we also need to pick an end site. So let's do end site 256. So now this will initialize our sky model from this chain. Okay, and let's inspect that real quick. So we now have a sky model at end site 256 with the following components. And you can also see here what spectral parameters these components have. So the components are stored in this dictionary. Okay, let's visualize some of the data in this sky model. So for that I will import heelpy. And let's check out an amplitude map of one of these components. So we access the component, whoops, let's say AME, and the amp map, this is the syntax for that, and then we just want the temperature. So let's also just normalize this to hist. That should be components. Okay. Okay, so that's what that looks like. Okay, and this map is made at the following reference frequency, frec ref. And you can also inspect the spectral parameters and plot those. So this will depend on the component, right? For instance, dust has 2 spectral parameters, beta and T. Okay, so that's how you can get to the data. That's essentially the data that's been loaded from the chain. But we can also use this sky model to produce simulations. And the way we do that is that we simply call the model. So doing something like this, just calling the model and passing in a frequency, that's how you produce a simulation. So before I do that, let me just import AstroPy units. Okay, so let's just quickly make a simulation at 50 gigahertz. So this will just print the array. Yeah. Okay, so what does this look like? Let's plot that. Okay, so this is what that simulation looks like. So you can see that we have the dipole is by default included. but we can disable this by calling the remove dipole function on the model. So let's do that. And if we try that again, okay, we see now that the dipole is gone. Let's try out some other features. So in addition to providing a frequency, we can provide a full width half maximum. So let's do 40 arcmin. Let's change the frequency just for fun to 100. Oh, my bad, that should be a u.arcmin. Okay, and that looks like this. It is also possible to change the output unit. So let's say you want, by default, it is in micro Kelvin K Rayleigh genes, but we can also specify, for instance, megajanskis per steradians. Instead of doing the entire sky, you can specify a single component. So the way you do that is with the components keyword, and that takes in a list of strings that represents a component. So let's do dust. We can also do radio. So this is the radio sources smoothed to 40 arc minutes. Okay, furthermore, instead of providing a single frequency, we can provide a list of frequencies. So what happens then? Let's do it like this. So what actually happens then is that it treats this as a bandpass integration. And if you don't provide an explicit bandpass, it will use a top hat bandpass by default. Okay, yeah. And you can also explicitly provide a bandpass. So let's say bandpass equals 0.3, yeah, something like this, and let's give that units of gigahertz -1. Yeah, and that works as well. Okay, so just to demonstrate an actual bandpass, I have now loaded in the WMAP bandpass for the K-band. And that looks like this. So these are the frequencies, and these are the weights. And so let's now try to plot that. And just to simulate WMAP a bit, let's use a beam of 0.8 degrees. And yeah, I think that's it. Okay, so let's see what, all right. This should have been, Okay, and that concludes the tutorial on the Cosmoglobe sky model.